So what we have seen is Gauss's law. And what we said is that you have a charge Q, you want the electric field E, and the way to go there is via Gauss's law. But as you can probably imagine, the application, for real life problems, okay, of Gauss's law is actually quite limited. Why? Because an object may not have a spherical symmetry. A line, a wire may not be infinite. Okay, a sheet may not be infinite either. Okay, and so if they are not infinite, then designing the adequate Gaussian surface and solving the problem is extremely difficult. Okay, so we have to invent other ways, okay, which will take into account the geometry of the object, but of course it has to be based on Gauss's law. It cannot be based on something else. Okay. And so, here's what we do. This is an arbitrary object, okay, that you see here. And it is charged with charge Q, okay? And the question is, determine the electric field at some point P away from this object, okay? So the trick, actually, is by assuming that this object is formed of tiny objects, is the sum of tiny objects, and each tiny object is a point source. So I have delta Q1, delta Q2, delta Q3. Each delta Q is a point source. But for a point source, the nice thing is that I know the formula. For a point source, my element dE is equal to dQ over 4 pi or epsilon 0, 1 over r squared. That is what we just obtained here. Here, that's for a point charge, for a point source. So I know it. So now what I'm going to do is I'm going to say that the electric field at some point P away from this object is the sum of all the electric fields caused by all the elementary charges. Okay, so this is what's shown here. E is equal to integral now over the charge object of dE's. And dE's, KE dQ over r squared r hat. And now the integration is not over a Gaussian surface, but over the actual object itself. Okay? And of course, the reason why I put it now, I insisted on doing this part now, is that one, I want to make sure that when you're applying this equation here, you have to remember this is a consequence of Gauss's law. This is coming from Gauss's law. Okay, it's not something which is on the side. Okay, so this is coming from Gauss's law. What we did is we used a mathematical trick, whereas a macroscopic object is divided into tiny element sources. Each element source is considered to be a point source. Since I know the electric field of a point source, then I can get my electric field for this object. And now my integration is no longer over a Gaussian surface, but rather over the object itself. Okay? So this is now a summary. That's what you see on the top. That's the electric field using Gauss's law. And the second one is the integration is not over Gaussian, but over the object. But once again, the KE dQ over r squared came from Gauss's law. Okay? So I have another problem here, but I don't know if I'm able to solve it. Just to give you a quick, let me see. Let me solve this problem here, and then we'll come back to these during, for example, the recitation hour. So I have an arc, okay? And the question is, get the electric field at this point P here. So if I take a small element of this arc, which I call ds, okay? This ds, it's negatively charged, then dE will be pointing towards it, right? This dE will have a dEx and dEy. Once again, we go to the projection, or we go to the summation vector according to the x-axis and to the y-axis. Now you can find another dE, which is on another element surface ds prime, which is dE prime, such that it has dEx and dEy. What you can see clearly is that if I now integrate over this whole arc, then the dEy will cancel out and I only have dEx, because here I have plus dEy and here I have another dEy. And for each of these elements, I have another one on the opposite side, giving me the other direction. So what's dEx? So my electric field is equal to dEx, integral from minus 60 degrees to plus 60 degrees, 1 over 4 pi epsilon 0. dq is equal to lambda ds, okay? And we can replace lambda ds. ds is going to be equal to r cosine theta, as it's shown here. This is my ds. So cosine theta, we will come back to that if you want next time. And I'm able to solve my problem to obtain this value here, or let's say this value. Okay? So all I want to say at this point is that in practice, we may be using this equation more often than the actual Gauss law. In this course, more emphasis is given on the actual application of Gauss law than on these integration, because I prefer to have to ask you about a conceptual question of Gauss law by really doing the integration. But nevertheless, you must know that these two forms will enable you to get the electric field at any point in space, okay, at any point in space, and consequently caused by some charge Q, whatever this charge form is. If the form of charge is symmetric, it has some symmetry, okay, then the easier way is to get Gauss's law. If it is not, then we actually need to integrate, okay?